Okay, so I know last time we kind of we spoke about the different t-tests, right? One sample, two sample, and pair t-test. And we spoke about like the differences of those two, how do we go about them. Um, we didn't calculate anything, but I do want to talk about, I guess, the difference between a z-score, a t, the different tables that you have access to, and how do you use them to your advantage, yeah? So like for this one, the one sample t-test, um, we're using one sample and we're comparing it to a population, right? Because we don't know the population standard deviation, we use a t-test, right? In this scenario, we're looking at, are the students getting less sleep than the average adult? So the null, right, is going to be that it is getting the same amount of sleep. And you can use that with words or with symbols, right? We say the mean, what would we say? Well, I organize my paper a little bit. The null hypothesis will always be, we assume what they're saying is true, right? Like the claim is what they're saying. And we just kind of go with what they're saying, right? The average adult gets 7.25 hours of sleep. So we're going to assume that that is true, right? You can say mu is equal to 7.25 hours. And you can write that, given that mu is the true value, right? And every time you write a null and alternative hypothesis, you're making an inference on the true mean or the true something, right? We're never going to infer on the sample. We're going to use the sample to make a statement about the mean. So we want to say the null hypothesis, what they're saying is true, right? The average adult sleeps 7.25 hours. The alternative hypothesis will always be whatever we're testing. And I'll make this with pen so it stands out better. Yeah. The alternative is this component, the question itself. Are students getting less sleep, right, than the average adult? So we're going to go and find evidence to support that the mean is actually less than 7.25. That's what this is talking about, right? We use the sample to make a decision about the true population. And then you would go, since it's to the left, when you're looking at your t-test, your t-table, right? This table is symmetrical, and you're only dealing with the right side of the table. So whatever value you get, you will move to the left, right? You're looking at like the left side. You can literally just look at the same values, since it's symmetrical, and then make it on the left side, because you're trying to test for this side of the population, right? You're testing for that. And you need to find your t critical. Now, what do we mean by that, right? We're talking about there's a critical value some critical value given the degrees of freedom, right, which is your sample size, you're going to have a threshold of what is like allowed. And anything below that threshold is in the rejection region. Yeah. So you find the critical value using this table, right? We look at your alpha, you find your degrees of freedom. Here it would be like 1.729, and I don't. Well, in this scenario, there's 123 students, right? So for this one scenario, your sample is 123, so your degrees of freedom would be 122. Now we're going to use a more conservative value of what? 100. Since 123 and 122 are not in here, we use the value that's more conservative. We don't round up, we round down here because we get more wiggle room in terms of like error, right? We rather reject it on the safe side versus the other direction where we round it up, and now there's a chance that we shouldn't have done that. Does that part make sense? So we would go there, we would look at our alpha is 0.05, and our rejection value is 1.660. That's our rejection value. That's the value we're going to be using here, 1.660 for our T critical. And we're saying, for this problem, we're going to calculate the T statistic here, right? We're going to calculate our own T statistic. And when you calculate the statistic, we're going to compare that to our critical. And what are we looking to hope for? Or what is it that we're trying to find? Evidence for what? We're finding evidence to support the alternative. So we're trying to see whether or not the T statistic lands in the rejection region. Compare it to the T critical, right? The T critical is a generic value that will work regardless of the sample. For that particular degrees of freedom, this is what's going to be acceptable. This is what is, the probability is too small, so we reject it, right? And then that value is going to change depending on the sample size, right? As the sample size as it changes, we have a different T critical value that we're going to use to reject. So in the T table, we are using a critical value to determine the rejection region. And this is where the alternative hypothesis lives, right? If we're saying less than, we're going to be shading to the left. You take your 1.729, but instead of doing it to the right, we're doing the same value to the left because it's symmetrical. So we would be using, in our case, negative 1.660 because we're doing less than as opposed to greater than. Does that make sense? We're looking at the tail probability. So whenever, and it'll tell you, right? Like here, we were going to assume that alpha is equal to 0.05 as our probability. So that's this region. This is 0.05%. Meaning, this critical value tells me what is 95% over here or more likely if it's greater than. But if it's less than this value, when we calculate our T statistic, then if it's smaller than that, we will reject it because the probability is too small for it to happen by chance alone. Is that okay? Now this is a one-sided. In a little bit I'll show you a two-sided t-test in a minute. And we'll use a different p-value for that one. Is this okay? Now, once you calculate the t-statistic, you really want to figure out, is it in the rejection region or not? If it's in the rejection region, we reject the null hypothesis. If it's not, we fail to reject the null hypothesis, right? If your t-statistic lands over here in the shaded part, we say we have convincing evidence to support the alternative that the adults actually sleep less than 7.25. The claim that they're saying is not really true. We have evidence to support this instead. But when it's not in the shaded region, let's say that your t-statistic lands over here, after you do your calculation, somewhere in this other space, we cannot have evidence to dispute this. So we're like, we do not have enough evidence to reject the null hypothesis. We don't have evidence to support this claim, this other component. We never say that the null is true, right? You're never going to want to say, since I didn't reject the null hypothesis, it must be true. That's not what we're saying. It's kind of like in the court of law, right? You are innocent until proven guilty. Just because you can't prove someone is guilty doesn't mean that they're innocent. You just couldn't find enough evidence, right? So you have to let them go. And that's the whole purpose, right? So the only thing you're allowed to say is if p-value is less than 0.05 in this case, right? We reject the null. We have convincing evidence to support whatever HA is, which in this case that they actually sleep less, right? And you want to say like a sentence of that. When you're using your conclusion, you're going to want to say like the true average amount of sleep that the adults get is actually less than 7.25, because we're trying to infer on a population. Now the p-value is not, right? This is the rejection region. Over here is in the not the rejection region. Yeah, if it lands over here, we say we fail to reject the null hypothesis. We don't have convincing evidence. To support whatever HA is in the statement. But never in this statement, in our conclusion, never will we say the null is true or the null is false. Never. Right? We can only support the alternative or fail to support the alternative. Right? We cannot, if we fail to have enough evidence to convict someone in prison, we can't claim that they were innocent. We just couldn't put them in jail because we didn't have enough evidence to say they were guilty. Right? Is that okay? Now this is the wording you're going to end up using for a z-test, t-test, proportion test, all that kind of stuff. Right? Once you find the probability of that occurring, that's what you say. Now here, in this thing, this is what I wanted to focus on. This right here tells me the t-critical. So you can say, since the t-critical, or since the test statistic is less than negative 1.666, we can reject the null hypothesis. Or if the test statistic is not less than 1.666, we fail to reject the null hypothesis. Because this table doesn't really tell us the probability of the event occurring. It just tells me whether it's at. Is it in the region or not? Yeah? And the z-score is different. This one actually tells you the exact probability of that thing happening for every single event. Yeah? You're going to use this probability in your z-table to make your decision. Is the number that I found less than 0.05? Here, you're not going to find an exact probability. You're finding a test statistic, and you're comparing it to the t-critical, the threshold that they give you that's allowed with that number of degrees of freedom, right? As the degrees of freedom increases, then you're given different thresholds amounts. And you're just trying to figure out, where am I in my statistic? So there's really two ways of doing it here, right? You can use a p-value, which can be found using a z-table, or you can use a test statistic, and compare it to your t-critical. Right? This is using your t, and in a little bit we'll talk about chi-square as well. The t and chi-square tests, sorry, I didn't even know I wasn't showing you that. The t and chi-square tests reveal a t-critical that you're comparing it to. This one is going to have a rejection region. Is it in the region that you're selecting or not? Yeah. While this one tells you the probability. You can technically also find the t-statistic for this one if you wanted, the z-statistic to the z-critical, and talk about the same way, but this one really focuses on the individual probabilities, right? As opposed to just a rejection region that this one holds. Is the difference okay? We're okay with the two differences? Okay. And then notice how this next example, is there a significant difference between smokers and non-smokers? Significant difference would imply that the alternative is not equal to the claim. Right? When it's not equal to is the difference that when they're saying, that's when we use a two-sided a two-tailed test. And you're going to divide the probability. Usually it's 0.05, right, for alpha. That's the most common one that they use. You can divide it by 2, so you can divide it into 2 equal portions. So now the probability would be like 0.025 and 0.025. Yeah, you're dividing that 5% error that's allowed. You're allowing that into 2 different sides because you're trying to see whether it's greater than or less than the claim. When it's not equal to, it's not here in the middle, it's something else, right? Or maybe the question is asking, is the amount of sleep greater than they're expecting? Then it would be a right-tailed t-test versus a left-tailed t-test. If it's a right-tailed t-test, well, you already have a right-tailed t-test here. It's just the right side of the table, right? We only have to change it when it's the left-sided t-test. And when we do that, we use a negative, we just change the t-value to a negative t-critical. Any questions with the tables, z-scores and t-scores, or t-table and z-table? Are we okay with that? How are we doing? Yeah? Okay. Now, let's talk about chi-squares here in a little bit, and then I'll show you what the chi-distribution looks like as well. Are we okay with conclusion component? On the next one, I want to talk about all the different types of tests, so you can organize your thoughts into like, how do you know which test to apply, right? And we're sort of are going to do that here today as well. So let's talk about chi-square. There's 3 different chi-square tests. Now the chi-square distribution is one-sided. This one is not symmetrical, right? And the chi-square distribution, you're using it for categorical data, right? Like one-way and two-way tables. I don't want to say just categorical data here because you can also use proportions for your z-table, right? Proportions, like a proportion z-test or a 2 proportion z-test. This is also categorical. But now you're dealing with a proportion, right? Like, is it different than the claim? The proportion of students, the proportion of males, is it different than the proportion of females? That's a little bit different. But when you're dealing with a one-way table or a two-way table, we're dealing with a chi-square distribution. And very similarly, we're going to find the critical value and identify if it's in the shaded region. But this one will only have one side shaded region. This is not going to have a 2-sided tail test, right side, left side. It won't have any of that. These tests are very different, and I'll show you how to think about that in a minute. Okay? Is that okay? Okay. So these are the 3 different chi-square tests that you have. You have the goodness of fit test, short for GOF. You have test for homogeneity and test for independence. The goodness of fit will have only one variable you're comparing. One variable. The most common example is that M&M example. You probably did it in class, right? You're given a distribution of M&M colors, right? You have the color like blue, red, green, yellow, etc. And you're trying to figure out in this one-way table whether or not the values that you have in your sample, do they match the claim? And in that example, I don't know, the claim was like 30% of the colors are brown, right? 20% are blue, 15% are yellow, right? You want to know if your sample differs a lot from that claim. If it differs a lot, you're going to get a chi-square value that's in this region. So your goal is to find the chi-square value of that test for each individual component, right? And that chi-square value, we want to know if it's over here. And it'll always be on the right side. It'll always be greater than the amount for this scenario. Is that okay? So goodness of fit. How good does the data fit the claim? That's how I think about it, right? How good does the data fit the claim? If it's pretty similar, you're going to get some value over here that is in the non-rejection region. If the values are really far apart from what they're claiming, you're going to get a really high chi-square value that's going to be over here. And then you're like, dude, something's wrong here. This is not what they're claiming to be true. Is that okay? Yeah. Now, homogeneity and independence, both of these are two-way tables. The calculation, the formula that you're going to use is the same formula for all three chi-square tests. It does not change. And we'll talk about it in a little bit. How do you do it, like observe? How do you calculate the expected? How do you find the degrees of freedom? All that stuff. But the difference here in your two-way tables is that there's two differences, right? How do you collect the sample? How do you collect data? And what are you trying to answer? What are you trying to like conclude or determine? That's really how I tell the difference between the two, right? Homogeneity. What does homogeneous mean? The same, right? When two things are the same. So here, you're comparing two or more populations. Two or more populations or samples. Are they different from each other, right? Are they the same? That's what you're trying to test for the test for homogeneity. So for example, let's say that you let's say that I want to compare the population of males and females, right? Males versus females. And the goal for males versus females is you're trying to figure out whether or not they are the same and how and which type of shoe they prefer. Yeah? Let's say that we're comparing Nike, Adidas, what other shoe brand? Under Armour, I don't know, Reebok, whatever, right? Like you have different brands of shoes and you want to know, is there a difference between the males and females in these distributions? You have two distributions. The males have their own set of numbers for which one they prefer. The females have their own. Do they differ from each other for the two populations? Or maybe you're doing it for middle schoolers, high schoolers, and college students. Do they like them the same way? Does that make sense? Is that part okay? We're trying to figure out if these populations are the same in the way that they are distributed, right? Maybe 20% of males like Nike. We want to know whether or not that's relatively the same for females. Is it also 20% for females? Is it 35% prefer Under Armour for males? Is it about the same for females? Do they differ from each other across the board? And we want to know if these two populations or more populations, are they homogeneous? Are they the same or not? And you will see the question, right? And I'll show you some examples in a minute. You'll see how the question is worded that will help you determine whether or not it is a test for homogeneity or independence. Now, independence, another word that they use is association. For this type of test, it's also a two-way table, right? You guys seen two-way tables and you're comparing like multiple things, rows and columns and stuff, right? You want to know whether or not the variables are the two variables related to each other. Is there an association between gender and the type of phone? Like, are those connected or are they really not? Are they independent of each other? Right? So for this one, you're going to collect one sample. Right? This is coming from one population. usually coming from a survey or something. Here you're comparing two populations, males and females. Here, you can also use males versus females, but you're comparing gender to shoe brand. So if we were to use the same example, here the variables we're comparing is, are these two associated at all? Is there a relationship between the two variables? While here, we want to know whether the two populations are distributed the same or not. And the wording is slightly different. The test is exactly the same. The chi-square value is the same. The rejection region is the same. All the math and everything's the same, but the conclusion is a little different. And the name of the test is a little different. Because now your wording is going to be about what you're trying to conclude, right? What are you trying to determine in the question? Does that help a little bit? So, one, categorical, goodness of fit, does it match what they're saying? For two, let's say that we have this. Here's another example for homogeneity. Let's say that we have M&Ms and we have Skittles. And let's say that we find that they have the same colors on both. They both have blue, they both have red, they both have yellow. I don't think there's like brown Skittles, but let's just assume that they are the same colors for both. And we wanted to compare whether or not M&Ms and Skittles are different by color. Does that make sense? So it's kind of like goodness of fit, but now you're comparing like M&Ms as their own population and then Skittles as their own population. Do they share the same percentage for brown? Do they share about the same percentage for blue? Same percentage for red, for yellow, for green, etc. Does that make sense? I'm comparing two populations. Here, I'm comparing two variables, whether they're related to each other or not. Is there a relationship between the two? Or is gender independent of shoe brand? It doesn't really matter. Right? Are those examples okay? Now, you're going to be calculating the observed. This is the data itself. Observed minus expected. This is the only thing that you really have to figure out yourself. The expected counts. The observed counts are usually given to you in a table format. They tell you the number of boys that like Nike, the number of boys that prefer Adidas, the number of boys that prefer Under Armour and Reebok, and they tell you the number individually, right? And your two-way table, you'll have to figure out your totals. This is like your marginal distribution that you spoke about in probability, right? What are the totals in the rows and in the columns? You're going to have to calculate the expected value. What are the expected counts for each cell? And that has a formula that you do row total times column total divided by your grand total, right? So you're looking at the row total, which is this number on the right. You're looking at the column total, which is this number right here. And then your grand total is over here, right? This is your grand or overall total. When you multiply the row total by the column total, where do they intersect? They meet here in the middle. This is the expected count that you're calculating right there. That's the cell that you're interested in, right? So to find the expected value for each of those cells, you would do whatever row it lands times whatever column it lands. You look at those totals and divide it by the overall total. And that gives you the other expected count. And you go individually to find all the expected counts. Yeah? Then, based on the table that they provide, you're going to find the difference. From the table, you subtract whatever expected counts you created. You're going to create your own expected counts table. When you subtract them, you square it and divide it by expected. And then you're basically adding them all over and over again, right? You're going to be doing observed minus the expected. And usually these expected counts are like different numbers, right? Minus expected squared divided by the expected for that cell, plus the next one, observed minus expected for the next cell, squared over the expected of the next cell, plus the next cell. The order of the cells don't really matter. And you just keep doing it until you add up all the cells, right? Sometimes you have like a negative value because it's smaller than expected. Sometimes it's higher than expected. That's what the square root is for. The square will account for the differences, whether they're positive or negative, which is why your chi-square statistic will only be one-sided, because all the values you calculated, whether it's a positive difference or a negative difference, will always be squared, which makes it always go to the right. Does that make sense? So once you calculate your chi-square statistic by adding all of these values up, you're going to compare the chi-square statistic, compare it to your chi-critical, your critical value. How do we find our critical value? Well, this is based on the degrees of freedom. And the degrees of freedom will always be row amount minus 1 times columns amount minus 1. Normally it's just n minus 1, right, for degrees of freedom, but here you're dealing with multiple columns, multiple rows. So if you had 2 columns, the vertical ones, you would do 2 minus 1 times however many rows you have minus 1. And the cross product of that, right, when you multiply those, you get your degrees of freedom, which will then take you to the side of your table, right? And usually for tables, you're going to be on the smaller side of things. You're not going to be given a table with like 17 columns and 36 rows, and you're not going to calculate some really big number, right? They're usually like 3 or 4 columns at most, and maybe 3 or 4 rows at most. And then you just figure out the probability. At what level do you want to reject the null hypothesis, right? So usually one of these, this is your range of values you're going to be sticking to. Yeah? How does that feel in general? The calculation here does not change. The expected counts does not change. The observed, the formula, the degrees of freedom, nothing changes for any of these tests. The only thing that changes is which test we're using, right? What is our conclusion going to sound like when we write it out? What is our null and alternative hypothesis going to sound like when we write it out? And we're going to assume that whatever they're saying is always true, right? So what are we going to assume for homogeneity? For males and females, we assume that there's no difference between the two, right? We assume that there's no difference between males and female distributions for the types of shoes that they like. The alternative is that there is a difference between the populations. And the chi-square value tells me whether or not the alternative can be validated or not, right? Can we reject the null hypothesis to support the alternative? And then for independence, what is going to be all null and alternative hypothesis in general? What is it that they're claiming, right, is the question. There is no association between the variables. Gender and shoe brand they're just 2 different variables that are like connected in this table. There's no relationship here. There's no association, right? The alternative is that there is, right? That we do have an association or a relationship between the two. And we find that by finding a large enough critical value to support that, if we do go there. Is that okay? Now let's look at some scenarios so that you can see how do I identify these, right? Let's put some context into it. You guys okay with that? Okay, so here are some scenarios, right? And I give you like this little packet, and there's different wording. Notice how we have a 2-way table. Is this going to be a goodness of fit? No, because goodness of fit is a 1-way table, right? Maybe if it looked like this, could be a goodness of fit because there's only one. But when the minute you have a 2-way table, it's going to be it's going to be homogeneity or independence. It's one of those 2 automatically. There's no other test that you can do. So you start to read the problem, you start to decide what they're asking, how did they collect the samples? What is the question really saying, right? Do these data provide convincing evidence at this level that the true distributions of color are different for the three different types. What are we comparing here? We're comparing distributions. Are the distributions different? What's another way to say that? If you're comparing distributions, are they all coming from one sample? No, they're coming from different populations. Different populations. These are separate samples. You're comparing two or more populations. And in this case, right, what are we comparing to them? This is going to be chi-square test for homogeneity. We want to know whether or not the populations are different from each other. So you can calculate your chi-square value. This is what I mean by observed. These are always going to be the observed table. Right? Here are the results of the survey or of whatever they conducted. This is your observed. You're going to create another one, and this is going to go in the part of the doing of your FRQ, right? Where you actually do one for like expected. And you create a table. What are the expected values that you see there? So you look at the row total, like in this case it would be row total, column total, right? 26 times 20 divided by what? 60. That gives me this first cell right here. That's where they overlap. That's going to be the first expected amount. So you do 13 minus whatever you got squared divided by whatever you got. All right, that's our formula. And you can find the expected for all these 6 values. There's 6 total different entries that we're interested in. Total times this total divided by 60. Total times this total divided by 60. And you can find your different expected counts so that you can do your chi-square statistic. Observed minus expected, over expected, over and over again for all 6 of these. Yeah. And then you can say, do I have convincing evidence to reject the null or not? Find the critical value here. What's it going to be for this one? What's going to be our degrees of freedom for this problem? Rows minus 1 times columns minus 1. How many rows do we have? 2. 2 minus 1 is 1. How many columns do we have? 3. 3 minus 1 is 2. 1 times 2 is 2. So my degrees of freedom is 2. At alpha level, 0.05. So what do? We go to 2 degrees of freedom, alpha level of 0.05. That's going to be the determining factor of my critical region, right? Is it going to be more than 5.99 when I do the math? If I calculate something more than the allowed, we reject the null and we can talk about the conclusion. Yeah? What about the next one real quick? What is this one asking here? We're given index finger, ring finger. Are they the same length? We're looking for males and females. What is this question asking? Does the data provide convincing evidence of an association between gender and relative finger? Association is another word for independence. They basically told us in the question, right, which test to use. And this one is chi-square test for independence. And they actually also tell you the expected counts. No need to calculate that. It's already in the parentheses. So you have observed minus expected squared divided by expected. Observed minus expected squared minus over expected. And you add all of those things to find your chi-square value. Right? The statistic. We just need to figure out the degrees of freedom, right? What is my chi-square critical value? What determines a rejection region? Well, the number of rows is 3, minus 1 is 2. We have 2 columns. 2 minus 1 is 1. Degrees of freedom is equal to 2. And the alpha level is 0.05. Right? They really like, in the FRQ, they really like a picture to determine the T critical of what is it going to be for us? Degrees of freedom is 2 at 0.05, 5.99 again. So when you write that right there, and you show a picture for like the rejection, and then you calculate your chi-square statistic is like, say it's, I don't know, 10, you can then like conclude something, right? Since it's like in my rejection region, or it's bigger than the critical value that's provided, or you can reject the null hypothesis, we have convincing evidence for the alternative. Right? So the key part here is, do we know the name of the test? And then you're basically saying the name of the test, the degrees of freedom, how did you find that value, the alpha. This is going to go all in your plan, right? State, plan, do, and conclude when you're writing your free response question. And if you miss some stuff, like this will always back you up. They're like, oh, that's what they're using to conclude it. If you forgot one, they'll see that this came from the table, which can be given credit when you're missing one thing. And then when you're very specific, it's really hard to not give you full credit in an FRQ, because you're like, man, this person found what they're looking for. They were able to support the claim. They were able to reject it. They were able to do all the things, and they're really happy, you know. And then lastly, here, we are not told how this data was collected. So, can we make an argument for the 3 different types of tests? First, look at the data. What are we working with, right? Online social networking. This is back in 2009. So, no Instagram, no Snapchat, just Facebook, and like other things, right? We're comparing, what are we dealing with here? Different age groups. And then we have people that use online versus not online. Yeah, do we have an idea more? That's what we're looking at? Okay, now let's talk about how this is not goodness of fit. Why would it not be goodness of fit? Yeah, we're dealing with 2 categorical variables. And we're looking for 1, right? We want to know the distribution of 1. And here we have multiple distributions that we're looking at. So, because it's not a 1 sample or a 1 variable that we're comparing it to a claim, this cannot be goodness of fit. What about test for homogeneity? How would you make it so that it is test for homogeneity? What would you ask? What would be the wording? Which ones are the populations here that you're comparing? And you can argue it for the rows or for the columns. You can argue for either. How would you go about it for test of homogeneity? Yes, that's a good way to say that, right? Is the distribution of the people that use social networks online the same as the people that do not? Are these distributions the same? That's if you're comparing online versus not online. How would you do it if you're comparing the groups over here? Is each age group distributed the same? Right? But I mean, which one would make more sense to ask? How are the age groups distributed? Are they distributed the same? Or the people online versus not online? As long as you know that, like, this will be more like a multiple choice question, right? Because you're now like selecting what's most appropriate, right? But yeah, I would go with that one where you're comparing online versus not online. Are they distributed the same across the board? We have 2 different distributions. Are they homogeneous? How would you talk about a test for independence or an association? I forgot how to spell association there. How would you do a test for independence? How would you word it here? Because for independence, we're comparing what? We're not comparing two distributions if they're distributed the same. What are we comparing? Or what do we want to know? Yeah, is it independent of age? We're comparing age groups, right? Is there an association between age groups and online usage? Are those two independent of each other? But now you're dealing with like big groups as a whole, right? Like all of that is kind of chunked into one. It's chunked into one, and you're comparing, is there a relationship between the two at all? Right? As opposed to, for homogeneity, you want to compare, how is this distribution, is this similar to this distribution? So it's all about the wording at the end of the day. And the math is the same. The only thing that would change is your null and alternative hypothesis and your conclusion. But everything else stays the same. So if you don't know, do all the math, do everything else, and maybe you get 4 out of 5 points for the FRQ. Because maybe you named the wrong test, but you knew exactly what to do, you just had the wrong wording maybe. But if you can identify from the problem, right? If you can identify from the question, right? Are the distributions different? Is there an association? Are they independent of each other? Let that guide you to which test to use. So we've talked about, can we tell the difference between which kind of test we're using t-tests? There's 3 different t-tests, right, that we spoke about, and there's 3 different chi-square tests. Next session, we'll talk about all of them to see if you can identify which test it is based on the question alone. Is this numerical? Is this categorical? Is this a 2-way table? Is this a 2-sample? Is this a 1-sample, right? And you can start to kind of categorize in your brain, organize yourself to see which test you're going to go about using. Because I believe they give you all the formulas, right? They give you all those things. You just need to know which one to use. And it comes down to what variable are you working with and how is it being sampled. That's going to be the biggest difference between all the different tests. Because I think all in all, there's probably like 10 tests that you can do, right? And the more organized we are with categories versus numerical, 1, 2 sample, what are we testing? Then the easier things kind of get organized in your mind. Was that helpful for today? Excellent. Thanks for coming. We'll see y'all next Wednesday.